Okay. So this is the introduction to digital logics. Let me just. And again, all these slides are online at that website. So to begin with, you have to understand what is the difference between analog and digital. So analog, which is what you'd be dealing with in the other introduction to electronics course, and analog circuits, that's where the value can be anything. So you have an infinite number of possible values here. So here we have a sine wave. And it can be, it can be 0 volts, it can be 1.2, 1.1, 2, whatever value you want. And in theory, it can take an infinite number depending how many decimal places you take it to. Digital just means it's discrete values. So in this waveform, in time, we're saying that what we consider its value is only of several possibilities. So here I actually have 3 possibilities. So here it could be 0. It could be this positive voltage here, or it could be this negative voltage here, but it's never in between. This state doesn't exist, we're claiming. So we're saying there's only those possibilities. And where digital comes about is literally digits, meaning fingers. And if you're counting with your fingers, you only have 10, assuming you have 10 fingers, only 10 possible units that you can count up to or through. You're either 0 or you're 1. There's no one uses half, really. So digital is very old. The abacus is an example of a digital. It's either, on this side or on that side. The in-between states mean nothing. Same with Braille is effectively a digital system. There's only certain values you can take. So a subset of digital is what we call binary. So binary is only 2 states. So the 2 states we use will either there'll be different names for them, but if we imagine a switch with a light bulb, the switch is either off or it's on, and that's it. So you can see the light bulb's off there, on there. Other names we'll give it, we might call it false when we're dealing more with the Boolean algebra. False and true, 0 and 1, so 0 being this off state, 1 being on, and low and high are other names we'll give it. But at the end of the day, it's all the same stuff, and all these 4 effectively mean the same thing as these 4. One thing that then you should be able to read into this is how we deal with binary waveforms in time. So you're probably used to seeing a sine wave moving in time along that axis and the value along this axis. But instead with binary, it's only 2 possible states, 1 and 0. So again, we have time going this way. Except here, the only possible states are if it's at this, it's 1. If it's at this, it's 0. So you can still say at time, t equals whatever, t equals 0, it's 1. At t equals 1, it's 0. T equals 2, etc., etc. So we still have the idea of time in binary, but at any point in time, there's only 2 possibilities for this value to be, 1 and 0. So these are just sort of alternate ways of looking at this same information. That this circuit goes to 1, then 0, stays 1, stays 1. And the top one's just a waveform version of it. So what we'll need to think about then is how we use binary and why we care about binary. And the reason we care about binary is because we can manipulate it easily with something called gates. And gates, as we have here, are basically just this magic hat. And you put in something and you get out something else. In this case, we put in binary data. So we put in a logic high, we're going to say. You can just arbitrarily give it, and you put in something else, say a 0, and you get some output. And you can put in different values, and you'll get a different output. So how we know what's going to happen is we use what's called a truth table. So for any particular gate, and we'll give it a name to the magic that's happening, say an OR gate, And we'll say that when either of those inputs is 1 or high or true, the output is always true. So if we had 0, 0 going in, we'd get 0. But as long as one of those is high, the output will be high. So if the other one's high, if this is 1 and that's 0, then it's still 1. So this logic we call an OR gate, and we write it down in a truth table. So here we just say for each input, every possibility, we give what the output is. So if the input is 0, 0, the output is 0. If one of the inputs is 1, or both of them, the output's always 1 in this case. So the name we give that is OR, because if one or the other is 1, the output's 1. And you can think of that, if you're building the circuit physically, it might look something like this. So we have 2 switches. If one of those switches is closed, power will flow and light up the bulb. So if that one's closed, power flows, lights up the bulb. That one's closed. And if they're both closed, it still lights up. So that's physically how you might build an OR gate. So when I show a representation of it, I'm going to be showing 4 things really now. We'll have a symbol here. And this is on schematics, how we're going to show what an OR gate looks like. So we have 2 inputs to it, A and B, and again, this is what we were showing here. I had called this one A and this one B. 2 inputs and 1 output. So in time, we have 0, 0, and 0. And this is shown on the waveform at this point. So we have 0, 0, and the output is 0. So that's here. Again, the next point, 0, 1, 1 for the OR gate is shown at this point in time. So we have 0 there, there's 1, and the output's 1. And you can read through that, your input's 1, 0, and the output's 1. And that's that line in it. So throughout the course, you'll sort of see all of these representations being used. You'll see the waveform style, and you'll see the truth table. So it's good to be familiar with all of them. And this final piece of information is the equation for it. So here the plus symbol is actually meaning OR. So in this class, for the most part, we're going to be dealing with what's called Boolean algebra. And Boolean algebra is just another way of writing down all of the same information. So you can either write this symbol that says it's an OR gate when A is 1 or B is 1, the output's 1. This way is saying when A or B is true, the output's true. So the OR gate's just one of several sort of basic entities we have. The next one is the AND gate. And the AND gate's output is high only when A and B are 1. So again, we have the same input waveform as before, except for the output, the only state where the output is 1, I should say, is this final entry here. So the output's 1 only when both inputs are 1. So using Boolean algebra, we have the output Y is A and B, and Y is true only if A and B are both true. So that's another of the basic gates. Sort of the final one of the 3 very basic gates we'll talk about is the NOT gate. And the NOT gate, the output is simply the inverse of the input. So when the input's 0, the output goes to 1. When the input's 1, the output goes to 0. So Y is not A, basically. And so here, we show this by just putting a line over it. So if we put a line over something, it means the inverse of the output is the inverse of the input.